Hi there, today I'd like to show you how to use an HP-7090A measurement plotting system to run a test. So instead of using the oscilloscope, if you have something maybe electromechanical that isn't that fast, you could get away with using a plotter to look at the data to characterize the system. So what I have here is a relay here, and this is a nice relay. You could kind of see through it, which makes it nice. And we'll get some close-ups of that pretty soon. And I have a nice switch, and I have a power supply here. So we're going to characterize this relay a little bit. I'm going to show you how to do that and how to use this plotter to look at the data. So here's a close-up of the plotter, and I have this power supply, and the relay is right here. If you could see that, it's a see-through relay, so it makes it a little bit easier to test and see what's going on. So we have some a lot of Pomona grabbers, clip leads. So we're going to turn this power supply on, and I'm going to do a sample run for you to show you how this works, how it's set up. So I'm going to turn on the power supply, and I'm going to set it to 12 volts. It's a 12 volt relay. So the way you do it is you push this display settings on voltage, and then you dial in 12. If this power supply loses power, you have to start this all over again. And there's one hassle with this, but it's for safety reasons. They want it to start off at low power. So we're dialing in 12, so we're getting it there, closer to 12, so that'll limit it to 12 volts. And then we're going to set the current here to 1/2 amp. So this relay doesn't take too much. It's a 160 ohm coil, so I believe it's a 72 milliamp relay. So the main thing is just to show you how this plotter works, using it instead of using an oscilloscope. So to switch the relay on, I have a nice switch here, and you might be able to hear a click. There it goes, it clicked on. And as you can see, it's about 0.08 amps. And now it clicked off. So I'm using a nice switch. For this type of test, you want to avoid any kind of switch that has bounce. So one of these old nice switches is a good way to avoid bounce. So one other thing I have here is I have what you would call shunt resistor. So it's a 1 ohm resistor, and that makes it very convenient. So 1 volt would be 1 amp, and 1 millivolt would be considered 1 milliamp. So it makes it easy to scale if you have a 1 ohm. If you can use a 1 ohm shunt resistor, sometimes in higher current situations you need to use a lower, like a 0.1 ohm. But in this case, being it's low current, the 1 ohm is sufficient. And then I also have a diode here, and I'm going to show you the diode on clips. So you basically, build your circuit using these clips. So there's the diode, and that's for the back EMF. So this relay doesn't have any diodes built into it. So when you de-energize the relay, you get a very big negative voltage if you didn't have this diode in there. So that prevents, it's a good design practice to put a diode in there so you don't get this big voltage spike. But it does have some consequences in that it slows the relay. It makes the relay a little bit slower. So if you need a fast relay, it's better not to have the diode. But if you could live with the slowness that the diode causes and it's not an issue, then it's better to have the diode in there. So next thing we're going to do is power up this plotter. And the plotter is powering up. It takes maybe 20-30 seconds for it to power up. So I have a setup already saved in the plotter. So I'm going to hit restore setup. And that'll get me closer to the conditions I need to record this data. So this plotter not only does a plot, but it also records data. So it can record 1,000 points per channel, and it has 3 channels, and the smallest time that it has is 0.03 seconds. So that would give you a 33,333 hertz update rate. So it has so it's pretty nice because you could vary the ranges. It goes up to 100 volts, which is much beyond what a normal oscilloscope will do. So by using these, you could vary the ranges, and it also has a trigger in it, so you could trigger off a signal, say like closing the noise switch. So when I close the noise switch, I'm going to trigger off of that and get a plot of the coil current, the voltage going into the coil, and also the action of the contact, one of the contacts on the relay. So I'm going to have a bunch of other data. I did a bunch of other plots earlier, and we'll show those and go through those to try to understand this better. Now this plotter has a holder that holds the pens, but in this one it has a mechanism called the Geneva wheel, and that Geneva wheel is broken, so I have to manually put the pens in instead. So I'm going to change it to the blue pen, and here's the blue pen. Right now the red pen is in there, so I could take it manually, just take it out and put it in the little arm there, and it would be nice to get that Geneva wheel fixed, but it's not worth it. I could just do it manually. So I'm going to put a piece of paper in here. So the paper uses this regular 8.5 inch by 11 paper. You can also put 11 by 17 inch paper in here too if you have to do some big plots. And you close that, and now the piece of paper is installed. So one thing you have to do is set the range of the plotter. So there's a way of doing that. It has a full scale point and a 0 point. So you want to leave some space for labels. So you could set that by hitting the shift key, and you could store it in the memory. So the first thing I want to do is draw the grid. So I made it a 20 by 20 grid. So all I have to do is hit the grid button here. I don't know if you can see me. I'm going to push the grid button. So there it goes. So it's drawing the grid. So the nice thing about this, it just uses regular copy machine paper. So it's nice in that it makes it easy to document things. With Oscilloscope, you don't usually get a piece of paper out. So this way, if you have a nice piece of paper, you could put your test results in, and you could put notes on to it. So I have the plotter set up. It's an internal trigger, so when I push down on the noise switch, it's going to put 12 volts into that coil. So I set my trigger level to 5 volts. So once it goes above 5 volts, it's going to record the data. Because this is pretty fast, you can't do this real time. You can also record things real time on this plotter, but for this speed, yeah, you would have lag, and it would cause errors. So this way you just fill a data buffer up. So the way to do it is you want to hit this fill button switch. So the light went on that says trigger. It says trigger search. So it's looking for the trigger. So that light will blink once it found the trigger. So I'm going to hit the switch. Here's the switch over here, and I'll tell you if the trigger went off. So I'm going to close the switch pretty fast because I don't want any bounce. So it went, and it just recorded the data. So it's recording 50 milliseconds of data to capture that action of the relay. So I'm going to open it up now, and you also want to capture the de-energization of the relay, not just the energization. And we'll go through some of these plots soon. So I'm going to plot out the first data. So what I have to do, because I don't have, because that Geneva wheel broke, I'm going to have to manually record each plot and change the color of the pen. So I'm going to hit these switches just so it plots buffer for channel 1 first. So I'm going to plot that out. So I hit plot buffer over here, and it should plot that plot. So that's the voltage going into the coil, and it was a very nice, if you can see the data, it's a very nice sharp looking curve. Now I'm going to change the color of the pen, and we want to plot out the current going into the coil. So I take the pen out, and I'm going to put the orange pen in, and this is the voltage across that 1 ohm shunt resistor. So each volt is 1 amp. So I'm going to hit channel 2 here now, turn off channel 1, and then hit plot buffer, and it's going to make a nice curve that represents the current. Eventually it levels off to about 72 milliamps. So now I'm going to plot the action of the switch. So I have a battery connected to the contacts of the switch, and I just want to change colors again to the red pen, and I'm using the battery rather than a power supply because I don't want the surges from the coil to impact the contact. I just want to read, I'm trying to get the delay time of the contact to see how fast this relay is. So I want to go to channel 3 now, and then hit plot buffer, and I'm going to measure. The nice thing about this, it gives me the delay times, the bounce, so you could see that red line going, and it's plotting out the action, so you could see there is some delay there. So the next thing I want to do is plot a label, and this gives me the settings of the plotter, which comes in handy looking at the status. So the nice thing about, so we're going to run that, you have to hit shift and label. Okay, so it's printing out the label, so it gives me all the ranges and the way the trigger was set. So it's nice to have this documented, so I could go back and analyze this. So it's nice to have the paper. I could use a scale on it, and you can really look at this data, review it, and try to get characterize this relay. So there's some important parameters of a relay you want to get that will help you with your design if you're going to use this relay in any type of application. So I got the label, and the next thing is to get a timestamp. So I hit shift, so I'm probably blocking the camera, and then you hit print time, and it gives me a date and a time. So that comes in handy also. So now I want to get some data points, and the way you do that is you hit this display, you hit the switch twice, display data, and you can switch between channel 1, 2, and 3. So I just so the way to get the data is you hit shift, print data, and it gives you a voltage and the time, which will come in handy. So that's for channel 1, and we're going to look at it for channel 3 here, which is the switch action. So I want to get kind of like all the breakpoints, and try to record that. So you can see this is the point. Okay, so the nice thing about this, it has what's called a pre-trigger. So although the plot from here to here represents 0.05 seconds, the first 0.01 seconds, the first 10 milliseconds, it's a pre-delay. So this way it triggered at that point, but it gives me the data before the trigger. So I want to look at it a little bit before it triggers, which is nice. So it's called a pre-trigger. So if you set that to a negative number, it gives you 10 milliseconds, before the event occurs. So I want to get this point here. This is where the voltage came in, and maybe I'll look at the current. You could see the current kind of comes up to some peak, and then as the contacts engage, it levels off to a final value. I know as these relays get warmer too, the current, the resistance goes down as it warms up, so then the current also goes down. So there's also other things like hold-in and drop-out currents and voltages are always good to get on a relay. In this application, for this one, we're not worried about that because it's just a straight 12 volts going in. There's no variation of that voltage. If there was a variation, then yeah, it would be important to get that. But for this, we're not testing that because in this application, that's not important. So you test the things that are important to your application. So the important thing is going to be to get the delay time, kind of the action of the switch. And so I'm going back on the action of the switch. You can see there's a little bit of bounce on that switch. So it also gives you some indication, what the bounce is on those contacts, which could be an issue. So you can really see, as the pen comes up, it bounces a little bit. But I guess this is the point where it finally settles in. So I want to get that. So that's pretty much it. We're going to take some pictures of the relay and the setup, and I'm going to draw a circuit. We're going to go through the data a little bit and discuss the data that was collected for this relay using this plotter. So this plotter is a nice tool if you have one. I don't believe they make these anymore, so you could do the same thing on an oscilloscope. I'm just doing this video to try to document how this plotter works, because I use it a lot, and it would help me to remember how this plotter was used if I have to use it. If I use it once a year for a special test, it would be good to look at this video, so it'll be easier for me to set up. But anyway, we'll look at this data and get some close-up photos. Anyway, this is the relay that we're going to test, that we have tests with the 7090A plotter. And the nice thing about this relay is it's see-through. You can see the coil and you can see the action of the contacts. So there's a normally open contact and a normally closed contact here, and you could actually see the switch move inside the relay. So it has a spring in it. So when you apply the 12 volts to it, the relay actuates and it changes from one set of contacts to the next. So this is the knife switch that we used to turn on the relay. And the reason why we use a knife switch is that it doesn't have much bounce, or very little bounce. More conventional switches, when you close them, they tend to bounce, where a nice knife switch, it goes in and very little bounce expected. So that's why we use the knife switch. So this is a battery that we used for contact testing, and so we'll run a voltage through the contactor, through the contacts of the relay. And we could just as well use the power supply, but because of transients from back EMF going to the power supply, we want to use something real stable. So this has got 3 AA batteries in it, so it puts out about 6.3 volts when you use this and you run it through the contacts. So this is a 1 ohm shunt resistor that we use for measuring the current. So it's good to use a 1 ohm resistor if you could get away with it, because the voltage is proportional to the current. And this is more of a power resistor, so we don't have to worry about warming up and getting a little higher in resistance as it warms up. So 1 volt would be 1 amp. Now in the case of this relay, it's a very low power relay with a 160 ohm coil that was measured. So it's about an 80 milliamp relay that would be going through this. So you would read 80 millivolts would be like the normal current when the coil is energized. So this is a diode that we used. We put it in parallel with the coil of the relay. And the reason for this is when the relay is de-energized, you get a pretty good jolt of back EMF due to the coil, the inductance of the relay. So by putting in this diode, you could get rid of that. We'll look at the plot soon and show why it does that. And but the only problem is when the relay de-energizes, when you put a diode like that in it, it makes the relay a little bit slower. It's not an issue if you're running a relay just open loop, but if you have feedback in your relay, it could become an issue. So if your application doesn't depend on time, yeah, it's great, you can put this diode in, but if it does depend on time, then it's possible that the diode could cause issues. So this plot here, this photo here, shows the overall results provided by the plotter, and it gives you a nice label, and you can go in and mark all the points. So it has some advantages over an oscilloscope. Of course, it can't go as fast as an oscilloscope, but it could go pretty fast. So we fill the data in a buffer so it doesn't have to plot out real time. Then we go back and we can look at the data. So you get 1,000 points per time axis here. You could also do XY plots and different types of plots with this plotter. It has a lot of flexibility. So it has some advantages over an oscilloscope, but you can also do this on a modern oscilloscope. You might not be able to get a good paper copy. You can print out the images on the oscilloscope, get a JPEG file, but sometimes this old school stuff has some advantages. So this is the power supply that we were using for this relay, and it was a 12-volt relay. So we set the voltage to 12 volts and we set the current limit to 0.5 amp. Yeah, you can see the little relay up here and the nice switch, part of the test setup. So you need a lot of jumpers to build a little circuit and plug into the plotter. So this photo here, it shows more of the test setup and the jumpers that you need. So it's good to have a good supply of jumpers, and you can build your circuit. It's possible to put this on some kind of circuit board or mount it to something, but I generally just lay it on top of the power supply. It's only a temporary thing, only a few parts, but it winds up getting a little bit of messy with all these jumpers. So we're going to talk about testing with an HP-7090A plotter as opposed to oscilloscope or electromechanical device such as a relay. Now this relay, the part number was OEG SRE-202D, and I did find a data sheet for it, but it seems to be an obsolete relay as of now. So the 7090A plotter can record up to 3 channels in time, doing a time history. You could also do an XY plot. You could do channel 1 versus channel 3, and it collects 1,000 points per channel. So its update rate depends on the total time selected. So you could select a real long time, say like hours, and a short time. The fastest time scale it has is 0.03 seconds, so that's 1,000 points. So it has an update rate of about 33,333 hertz at max. So this might be more convenient for testing a slower device such as a relay, and it gives you a nice paper copy that you can write on. So we're going to talk about some of these plotted results of this relay. So the first plot I did was I energized the relay and I recorded the 3 channels. So the one channel I recorded was the voltage going to the coil, and the second channel is over here. This is the current going through the coil. And the third channel is this normally open relay contact. So the nice thing about having plotted data is that you could draw the circuit on the plot. So this is basically the circuit. So we have the power supply, which is set to 12 volts and 0.5 amp. And we push down the nice switch, and this is the voltage going to channel 1. So when you push down the nice switch, the 12 volts comes through. So this is where the 12 volts is picked off of. So we have this 1 ohm shunt resistor, and we're reading the voltage across that, and that's the current over here. And on channel 3, which is the red line, this is called the normally open. So we call it NO contact. So normally when this is the de-energized state of the relay when it's unpowered. So when you power the relay, it actuates the switch. So as you can see, there's a bit of a delay from when you energize the relay to when the switch closes. So we measured this on the plot. It came to 8.5 milliseconds when you energize it. So the way you get it on the plotter, we plot this point here, which occurred at 0.0101 seconds, and we plot this point here, which occurred at 0.186 seconds. So we take the difference between the two, and this delay here becomes 8.5 milliseconds. So the current has some interesting dynamics. It comes up, and then as the relay actuates, there's some back EMF. So the current comes down due to the velocity of the mechanism moving, the solenoid moving, and then once it sets, once it pulls in, then the current comes back up again, and this is the the running current, which is 72.9 milliamps. Now generally as the relays heat up, the resistance becomes higher and this current drops down a bit. So there's many other characteristics that you can measure on these relays, such as the pull-in and drop-out voltages. In this case, we didn't need to measure it because for this application, we just put straight 12 volts on it, so we're not worried about the pull-in or drop-out voltages on this. So when you run a test, when you characterize something, you do it for the things you want to test, and things that you don't have to test, you could just ignore. Now in the next plot, we de-energize the relay. So in that case, this noise switch is already closed, and we open it. We open the noise switch. So we had to reverse the trigger. So these are the settings on the plotter, the range. So when it says 100, it's 100 volts going across here with an offset of 80. The current here is 400 millivolts with an offset of 0.2 volts. And for channel 3, it's 40 volts across with an offset of 10. It's good to have different offsets here so the traces don't overlap, so you can offset them by that and to try to maximize the dynamic range that you could have. So likewise, this blue line is the voltage across this coil. Over here is channel 1, and the orange line is the coil current. So it starts at the 72.7 milliamps, and when you open it, of course, the current goes to 0. And this is the normally open contact, is the red line here. So in this case, what happened, there's no diode in here at this point, so you get a huge spike, voltage spike. I was reading it goes to minus infinity, but we read up to minus 111 down here. You could see the point there. So when we open this noise switch, because of the inductance of the coil, the voltage drops down negative, very big. And also the current, it impacts the current. So it's always good to put a diode. So from doing this, we identified that we needed to put a diode in here to get rid of the spike. So so we saw before we had an 8.5 millisecond turn on time, but the turn off time is very fast. So we measured that to be this delay here, this 0.0130 minus the 0.001. The 0.01. So we're reading 3.15 milliseconds. Now one other thing with the plotter is you could set a pre-trigger on it. We talked about that a little bit earlier. So although the total time here is 50 milliseconds, the first 10 milliseconds is recorded, and it triggers off the trigger is this is over here 5 volts. So when this drops below 5 volts, it records the data. So it's called a pre-trigger. So by setting that to minus 0.1 on the plotter, it records the data for 10 milliseconds before the event. So we captured that. So that's a nice feature to have. A lot of oscilloscopes also have that. So this is another little twist on it again, where instead of measuring the current across that shunt resistor, we since we only have 3 channels, we moved channel 2 from the shunt resistor to the normally closed contact. So the thing we were looking for is what I call this dead time. There's a point in time when this contact transitions that it's neither one of these are closed, it's open. So that's good to get to know. So there's a battery in here, that 6.3 volt battery. It's 3 AAA batteries. So you can see as the relay is energized, this is the normally open contact closes, and we read this 6.32. But of course, the normally closed contact opens. So this contact opens, and this one closed. But there's a point in time here called the dead time when they're both open. And so you could tell these contacts are called break before make. So you could specify relays to be, rather than break before make, you could specify them to be make before break, so you don't have any of this happening. So in this case, there's a point where there's no load on the contacts where they're both open, and that could be a disaster for some applications. So you want to depending on your application, you need to know, do I have a make before break or a break before make? And you can also get time delay relays that have controls on this delay. We got well the normally open switch was at 7.7 milliseconds, and normally closed was right as 5 milliseconds. So the difference is this dead time was close to 3 milliseconds. So we know so you could also specify time delay relays where you could specify how much time you want these contacts to have. And there's also a little bounce here on that contact there, you could see. So the next plot here is when we de-energize the relay. We did this previously on plot 2, except now we put the diode in there. So now when this turns off, we don't get that huge spike. So we got rid of the back EMF. So that makes a much nicer plot, and the behavior of the diode is behavior of the relay is much better. So the blue line again is the coil voltage, and the orange line is the coil current, and the red line is this normally open switch. So we still have the delay, but the interesting thing, now when we de-energize the relay, we get close to 12 milliseconds. We measured 11.9 milliseconds, where before it was only 8.5 milliseconds. So from adding this diode, it slows the relay down when it de-energizes. And we notice when we energize it, the diode has no impact. It's only when we de-energize it. So you have to be aware that if you add a diode, it does change the characteristics of the relay slightly, and makes the relay a little bit slower on when it de-energizes, but it does get rid of the spike. So depending on your application, it might cause you some issues. And now in this plot, we wanted to energize the relay again, but with the diode. Plot 1, we energized it, but we didn't have the diode in there. So it's a 1N4001 diode. I believe that's like a 1 amp diode, and because our current is much smaller, it's only 73 milliamps. So anyway, so when we add the diode, we notice the same behavior. There isn't much difference on the make time, the time it takes from the voltage gets applied to the relay to the time the normally open contact closes. So it's still running around that 8 milliseconds. So the diode doesn't impact when you energize the relay. So in the next plot, we wanted to look at the contacts again. So rather than have channel 2 as the current across the 1 ohm resistor, we were looking at the normally closed switch. So this is energizing the relay again. We're applying the 12 volts to the relay, and we're trying to look at this dead time again, and with the diode, and we notice that it's the same. It's running about 2 to 3 milliseconds, and when you energize, the diode doesn't impact the relay. It's only when you de-energize it that it adds a little more delay to the action of the switches. So that was the purpose of this plot, and so there is some dead time. So this is a break before make type switch. So the last plot we have here is where we de-energize the relay with the diode in there, and we notice that the time it took for the normally open contact to disengage was longer with the diode. See, the relay isn't as fast when you de-energize it. Of course, you don't get the big spike in voltage anymore. So, but the interesting thing that was noticed was the normally closed contact has a lot of bounce. I guess I call a fuzzy dead time, because as it's actuating to provide the voltage through it. So what's happening as we open this nice switch, this contact moves down. This normally closed contact. So what's happening here? The relay is de-energized, so it goes back to this contact here, and that seemed to have a lot of bounce in it. I guess what's happening is that the spring is uh, not so good, and it's the electrical force is overcoming the spring force, and it's a light force on that contact, so it bounces quite a bit, which could be an issue depending on your application. So you might need to put debounce software in there if it's a software function, where it could cause some kind of chatter. So anyway, that was the last plot. So it's good to get this on relays if you're involved in the design of electrical system and you want to dig into the relays. There's a million things you could test that would give you more insight to avoid issues. So anyway, this thing was more of a demonstration of the 7090A plotter, the HP-7090A plotter, but it's also a good demonstration on how to test relays. So anyway, I hope you like this, and hopefully this gave you some insight how to make the HP-7090A plotter work, and how to go about testing an electromechanical device that has voltage and current, such as a relay. Thanks for watching this. Bye now.